interesting features of quadratic equations. I don't know if you can remember this, but we've solved quadratic equations in many ways, and we've often got positive numbers underneath the radical. There's the quadratic formula, and when we did and we graphed that, we found that the parabola, or the graph of the quadratic equation, intersected the x-axis 2 times. So it was a U-shape and it crossed the x-axis twice. When we got a negative number underneath this radical right here, we had an imaginary number. And what we're going to discuss now is how many solutions you have to a quadratic equation and what form they're in. Well, when there's an imaginary number there, that quadratic equation doesn't cross the x-axis at all. There are 2 solutions to that problem, but there's an imaginary term, or we say there's 2 complex numbers as solutions to that equation. And then finally, if the number underneath the radical ever turned out to be 0, then what we would be doing is we'd be taking the opposite of b plus 0 and dividing by 2a, and then the opposite of b minus 0 and dividing by 2a, and we'd have the same answer. So that's a situation where there's just one solution to the quadratic equation. If I graphed it, the vertex of the parabola just touches the x-axis in that one spot where the solution is. I'm going to try to illustrate all 3. Here's the first. If I want to solve x squared plus 12x plus 36 equals 0, I'd just like to remind you real quickly that I could solve this by factoring. And there would be my 2 binomial factors, and the zero product rule says let x plus 6 equals 0, let x plus 6 equals 0, and solve for x. Well, x is a negative 6 here, and x is a negative 6 here. Well, we call that a double root. I don't need you to write it down twice. That is the solution. If I were to put a 1 and a 12 and a 36 into the quadratic formula, here's what I really care about now that you recognize. The opposite of b, the opposite of 12, plus or minus b squared minus 4 times a, which is 1, times c, which is 36, all divided by 2 times a, which is 1. And this is the only time I think I'm going to solve this whole problem. What I care about here is that you notice that underneath the radical, you have 144 as your first term, minus 144. So the discriminant here is equal to the 0. The square root of that is 0, and the square root of 0 is 0. So what you have here is a solution that reads a negative 12 plus or minus 0. Well, that's just a negative 12 divided by 2. So that solution is just a negative 6. Again, same solution as we got here. And finally, a quick sketch. If we were to graph this, and I'd like you to do this at home, this point right here, where x is equal to a negative 6, is where the vertex of this parabola will touch, and it will go up in this direction and up in this direction. That'll be your U shape, and it will just touch at that point rather than crossing in 2 points. We've shown you 3 ways to solve this equation, just to remind you. But all I care about here, when I ask you what's the nature of the solution, I need you to tell me that there's one solution, and it's because this right here is the square root of 0. That's why there's one solution, and it's a real number. All right, it's not imaginary. It's going to touch the x-axis. So that's what I'm looking for. What's the nature of the solution, not necessarily what is the solution. And I want you to be able to tell me that there's only one, and it's a real number. Here's a different problem. It's going to have 2 real solutions. I want to look at the value of the discriminant and discuss that. So in this problem, a is equal to 4, b is equal to 8, and c is equal to a negative 5. I haven't even checked to see that these can be solved by factoring, because I'm really curious about what's underneath this radical here. So you would say in the quadratic formula then here that I want the opposite of b, which is a negative 8, plus or minus the square root of b squared, so 8 squared, minus 4 times a, which is 4, times c, which is a minus 5, all divided by 2 times a, which is 4. And I simplify this, and what's under here is 64 plus 80. That turns out to be a positive number underneath the radical. So again, there's 3 situations we're going to encounter. One is where all of this is 0. The other is where this adds up to be a positive number, and in this case, that's the square root of 144. So we have a negative 8 plus or minus 12, because the square root of 144 is 12. And you're going to get 2 real answers to this problem. A negative 8 plus 12 is 4 over 8, or 1/2. And a negative 8 minus 12 is a negative 20 over 8, or a negative 2.5. There are the two solutions. What I'm asking of you is to just be able to tell me that because the number underneath the radical here, the 64 plus 80 is positive, tell me that there are two real solutions. That's all I want to know, is because that's positive. However, just wanting to illustrate, if you were to graph this, this is going to look something like this. That point right there is the negative 2.5. That's this. This point right here is the 1/2. I can see that this is going to look something like this if you were to graph it. And you would find that the two solutions are where the graph crosses the x-axis. But again, because that's positive, I want you to be able to tell me that there's two real solutions. The last example, in terms of telling me the nature of the solution, there are only three types of situations. One where the number underneath the radical is 0, so there's one real solution. One where the number underneath the radical is positive, there's two real solutions. And next, this is going to be an example of the value underneath the radical, or the discriminant, is negative. Then you're going to tell me if there's two complex numbers as solutions. That's going to be an imaginary number. Here, A is equal to 1, B is equal to 3, C is equal to 4. I will then have the opposite of B, which is a negative 3, plus or minus the square root of B squared, minus 4 times A, which is 1, times C, which is 4, all of that divided by 2A. Again, all I really care about is this discriminant. It is equal to the square root of 9 minus 16, or a negative 7, all over 2. And again, if that's the case, if you have a negative number underneath there, you need to tell me that there are two complex numbers as solutions. I'm just wanting to know the nature of the answers. Now, that is the answer, although I would like you also, remember, to put the I in front. I like to put it in front. Our book puts it in back. But pull out the square root of a negative 1 there. Again, please remember, in summary, three situations. A 0 underneath the radical gives you one real solution. A positive number underneath the radical gives you two real solutions. And a negative number underneath the radical gives you two complex numbers as solutions. This next objective is very fun, in my opinion. What I'm going to do is I'm going to give you two solutions to a quadratic equation, and I'm going to ask you to do the reverse, and that is write the quadratic equation that has those solutions. Well, what you're going to be doing is the backwards version of the zero product rule, and then some algebra skills. That's it. Let's say I said to you, find the quadratic equation that has two solutions. One is a negative 5 and one is 11. Well, what you need to do is you need to write these statements. If I say to you, find a quadratic equation where one of its solutions is x equals a negative 5, then write that down. And the other solution is x equals 11, then write that down. And what you've got to do is you've got to get these two statements equal to 0. So in this case, I'm going to move the minus 5 over to the left-hand side and write that as x plus 5 equals 0. And here, I'm going to get the 11 over to the left-hand side and write that as x minus 11 equals 0. The reason I did this is this kind of looks like the zero product rule, but towards the end of it. The zero product rule says that if you have two or more factors, and in this case, the x plus 5 and the x minus 11, and if they are equal to 0, then the other of them is equal to 0. So again, we've gotten to this point in the past and we've gone here and said find the solution for x. I'm working my way back down. And now all I'm going to do is algebraically I'm going to FOIL this. I'm going to multiply these two binomials out. So x times x is x squared. Here I have a minus 11x plus 5x, that's a minus 6x. And 5 times a minus 11 is a minus 55. I'm done. That's the equation right there. X squared minus 6x minus 55 equals 0 that has this and this as a solution. It's pretty simple. Another problem, the same objective. Find a quadratic equation that has these two solutions. So again, first, would you write down x equals each of those solutions? And then would you get the constant onto the other side of the equation? So here I'm going to have x minus 3/4 equals 0. And here I'm going to have x plus 2/3 equals 0. What I would suggest you do at this point, unless you can see this, is I would go ahead and I would multiply both sides of the equation by the LCD. So I'd multiply this by 4, I'd multiply that by 4 and that by 4. Well, what that gives me then is 4x minus 3 equals 0, because those 4's cancel out. Well, just think about multiplying everything by 3 here. That'll become a 3x. When you multiply this by 3, it becomes just 2 equals 0. It's that simple. And then these two binomials, 4x minus 3 and 3x plus 2, are part of the quadratic equation that will be composed that has these two solutions. And now I will just FOIL this. So here I get 12x squared, and then 4x times 2 is 8x. Here I have a minus 9x. Those add to be a minus x, and a minus 3 times a positive 2 is a minus 6. And I'm done. This is the quadratic equation that has these two solutions. Writing a quadratic equation that has two imaginary solutions is no different than the previous two problems. So I want to have the quadratic equation whose solutions are 7i and a minus 7i. So I'm going to get this 7i on the left-hand side, so I'll have x minus 7i equals 0. Here I'll have x plus 7i equals 0, and then I will write the product of these two binomials. Because the zero product rule tells me I can do so, and now I'll FOIL this, so x times x is x squared. Please notice this 7i and that minus 7i, x in each case, add to be 0, and a minus times a positive is a minus 49, and I times I is I squared. Please don't forget that I squared is equal to a negative 1. So a minus 49 times a negative 1 is a plus 49, and there's your quadratic equation, x squared plus 49 equals 0, that has these two imaginary solutions. And just recognize that any equation that has an x squared term is considered a quadratic equation, and so that is the correct solution. Now we're going to solve some quadratic equations that are quadratic in form but just don't appear to be. They just don't look like it at first. You have to be creative. You have to be very creative in these problems. I have an equation that's x to the 4th power. That is not x squared. Quadratic is x squared. I have a middle term. It's got an x squared term. So here's the creativeness. If you would think of x to the 4th as x to the 2nd power raised to the 2nd power. Remember, the shortcut here is to multiply the 2 times 2. That gives you 4. And do nothing else with the rest of this equation, but now you have to state a premise for yourself. I'm going to use a different letter. I'm going to use the letter u, and I'm going to say, let's replace x squared, that expression, with the letter u. So right here, that x squared, I'm going to replace with the letter u. I'm going to remember it for later. So what I have here is no longer x squared raised to the 2nd power. I have u raised to the 2nd power. Well, given that premise over here, if x squared is the letter u, then this right here should be replaced with the letter u as well. And what I now have is a quadratic equation that I need to solve. This one happens to be very simple to solve by factoring. So I'm going to do that and just check it. Look at, yeah, it looks all right. And so u minus 4 equals 0 and u minus 3 equals 0. So u has got to equal 4 and u has got to equal 3. But remember, u is x squared. So come on over here and say, I'm looking to solve for x, and I know that x squared is equal to 4, and x squared is equal to 3. And the principle of radicals says that I should take the square root of both sides now and find out that x is equal to plus or minus 2, and here as well, and x is equal to plus or minus the square root of 3. And there are 4 solutions to this particular equation, and it's because it's an equation raised to the 4th power. Now, there are not always 4 real solutions, but in this case there are 4 real solutions to this equation that has a 4 as its exponent. They are plus and minus 2, and plus and minus the square root of 3. Here's another example of an equation that is quadratic in form, but it's not real apparent at first. What I would highly suggest to you is always use the letter u, because it's something we don't use very often, and that helps make it clear to you that you're replacing it for an expression in the original. Also, would you look to the middle term here? In this case, it's a minus 4 times what's in the parentheses. That's what you always let equal to u. So I'm going to put right in the middle here that u is equal to 2t squared plus t. Because if I do that, over here I have 2t squared plus t, and I'm going to have that, which is u squared. So I have u squared minus 4 times, this is u, plus 3 equals 0. And I see that this can be factored. Looks like a -3 and a -1. And you're using the zero product rule. I'm not going to actually write the whole thing. That would be u is equal to 3. This would be u is equal to 1. Now, u is equal to this, though. So I have to come over here and I have to say that replace u with 2t squared plus t, right there, equals 3. And then now I'm going to bring the 3 over to the right-hand side, left-hand side. I'm going to do the same thing over here. I'll have 2t squared plus t equals 1, and that will be 2t squared plus t minus 1 equals 0. And now I've got quadratic equations to solve. It's quite interesting. So I'm going to factor this into the product of two binomials, and I'm going to do this not using the alternative method in my head. So I think I'm going to need a +3 here and a -1 there. Yep, that looks good. Let's finish this up. When I set this equal to 0 right here, I'll subtract 3 from both sides. I'll have a -3. I'll divide that by 2. That's one of my solutions. This right here, when I set that equal to 0, t is equal to 1. Over here, I'm going to factor this as well. So I have 2t and t. And I think I'm going to need a +1 here and a -1 there. Yep. And so each of these will be set equal to 0. I'm going to do them in my head, though. This one will give me a solution right here. I'll move the 1 to the right. It'll become a +1, and then I'll divide it by 2. Here, I'm going to get a -1 as a solution for t. Here are my 4 solutions to this equation that is quadratic in form, again, not apparent, and I had to use some substitution in order to do this. I'm going to close this section, which is titled More on Quadratic Equations, with one more problem that is quadratic in form but is really not apparent at all. Remember, the very last problem I shared with you, I suggested that you take and let u represent the variable raised to some power or the expression other than the coefficient here. So would you let u equal x to the 1/3 power, so that right here you could call that 2u. If u is equal to x to the 1/3 power, then if I squared both sides of this statement, then u squared would be x to the 2/3 power, because 2 times 1/3 is 2/3. So I get to come back over here and take this x to the 2/3 and replace it with u squared. And this x to the 1/3, I get to replace it with u. And I now have an equation that's quadratic in form. And again, this one happens to be factorable. And you know, we're trying to keep it from, this is the part we want you to get here. We don't want you to have to spend a lot of time on quadratic formula and all. So it looks like I need a +4 and a -2. And then u plus 4 equals 0. I'm showing you the steps this time. I have a little bit more room to do that. So u is equal to a -4 and u is equal to a +2. Remember though, u is equal to x to the 1/3 power. So in each case, I'm going to replace u with x to the 1/3 power. And in order to make that become an x, I'm going to cube both sides of this equation to solve for x. So right here, again, I did it because 1/3 times 3 is 1, and I wanted that to be an x to the first power. A -4 cubed is a -64. There's one of my solutions. Right here, when I cube both sides of this equation, again, I'm going to have x on the left, and 2 cubed on the right is 8. There are my 2 solutions to this equation. This concludes this section again, more on quadratic equations. We had to here learn about the discriminant, the value under the radical. We had to learn to take solutions to a quadratic equation and write the equation itself. And then thirdly, our last objective was to take quadratic equations that appeared to be quadratic in form and solve them using kind of some unusual methods. In this case, letting u represent a part of the expression.